This was one of those bits of science that I ran into, and it's pretty mind-blowing, and I never hear anybody talk about it. I think this would definitely be worth putting some resources into to try to figure out how rigorous this was in using a whole group of scientists rather than just one scientist's life research. Because if it's just one dude's life research, it's easier to just toss it away. But if we have a whole group of us looking at this and verifying or disproving what he said, I do think this would be really valuable. So the particular guy in question is George Dodwell. He was the government astronomer for South Australia from, I think, 1909 until 1952. And the reason I'm familiar with George Dodwell is because Bernard Brandstater, who many of you knew, met George Dodwell when he was a medical student in Adelaide, in Australia. That was toward the end of Dodwell's career. And so he was able to talk to Dodwell about this. And the reason we have the manuscript is because Barry Setterfield got a hold of it, and it's up on his website. So this book would also, I think, be worth editing and publishing. So this is the basic science behind this. All the forces that affect the Earth are tidal forces and depend on the equatorial bulge of the Earth as a lever to affect change. So the gravity of the moon, the gravitational attraction of the moon, of any object, decreases by the square of the radius between the two, right? So if you look at that graph, the moon's gravity is stronger on the side of the Earth that faces the moon than it is on the opposite side of the Earth. And that allows the moon to have some effect on the Earth over years and thousands of years. That is incidentally why the moon's tidal force is so much stronger than the sun's tidal force. Not that the moon's gravity is stronger, but rather that the tidal force is stronger. If you were to think of this as being the sun, and then we'd be way far out on this graph where the amount of gravitational attraction between the front and back of the Earth is very small compared to the moon's tidal force. So these forces produce several cyclical outcomes which have been carefully measured and calculated and are well understood. So there's a 19-year cycle that is nutation, and you can see the arrows pointing in the direction of the movement. Precession, and another nutation, which is a 41,000-year cycle. Sometimes it can be hard to imagine the effect of a very small force over a long period of time, but this ion engine, it produces between 2 and 9 grams of thrust, 4.36 grams average. And so imagine, maybe like a sheet of paper or something, like that much thrust on a large spacecraft, on a fairly large satellite, and it can accelerate it by 4.5 kilometers per second over a long period of time, over 20 months. And the transit of Venus, I got that picture several years ago, and I think it must have been, that was 2012, yeah. And that exerted Venus was exerting 1 milligram of force on every human at that point, approximately. There it is, with some sunspots. Okay, so the axis of rotation was known to shift, but the forces involved were not understood. Newton explained that the phenomenon was gravitational in Philosophiae Naturalis Principia Mathematica in 1687. Stockwell formulated and published an excellent approximation in 1872, and then Newcomb perfected the formula for our time and the several thousand years on either side of us in 1897. And Newcomb's formula was used until I believe it was 1983, at which point the astronomers had better tools. And you can go on Wikipedia and see the exact formula that they use now. So, okay, Dodwell died in 1963, 1879, 1963. He was born in England but lived in Australia most of his life. Yeah, so he was a government astronomer for South Australia between 1909 and 1952. And he spent a lot of his life collecting and analyzing these ancient measurements. And the measurements were often taken with these tools, the gnomon, and you can see one here. It's just a couple of sticks, one on the ground, one standing up. And using it, you can chart the path of the sun through the sky. So here's a Chinese gnomon. Here is an Egyptian obelisk, which had this could be used in the same way. They put the ball at the top for precise measurements. This obelisk was 230 tons, and it was brought to Rome in 357 AD, where they broke it into 3 pieces, and then it was restored many centuries later by Pope VI the Fifth, which is a funny name. Okay, so when Dodwell collected all this data, you can see Newcomb's formula there, and so imagine Newcomb's formula coming off and just making a sine wave that heads back across the wall. Just kind of in like kind of a range here, but then look at what the data actually do. I'm going to try to get, so you can see we have an awful lot of, there's an awful lot of data points very close to the modern era where they were doing a lot more astronomy. But then there's data points. There's one data point out here, but there's a lot of data points. There are a lot of data points right along this curve right down here. We have one down here, and we have another way down here. So there's quite a bit of data, and this comes from Greece, from India, from China, from a lot of other ancient sources. If you look at the date, this is 0, the year 0. So we have quite a few BC dates up to 1000 BC here. And notice also that the graph doesn't stabilize until almost the modern, almost our time. Dodwell predicted, according to Dodwell's calculations, it stabilized in 1850. So beyond 1850, measurements deviated from Newcomb's formula in a very predictable way. So Dodwell did some more work on this, and this is the curve that he eventually came up with. It is a log sine curve plus the oscillations plus Newcomb's calculations. The oscillations are typical of recovery from a wobble, and the point at which the log curve goes flat is the year 2345 BC. The other end of the curve is 1850 AD, where the obliquity of the ecliptic ceases from deviating from Newcomb's formula. So this is a really interesting case study. This is the Great Solar Temple of Amun-Ra at Karnak, Egypt. And, okay.
Back up a couple of slides.
Back to this.
Okay, time is on the vertical axis.
Yeah. Time is on the horizontal axis.
Well,
Sorry,
okay, time is horizontal.
Yeah, so time is horizontal, and this is, sorry, the numbers are really small, sorry. So this is 24 degrees obliquity. This is 25 degrees, 23, 23 and some, about where we are now. So we actually have data going past 25 degrees. Yeah, so obliquity versus time here.
Okay.
And the dates here are from 2345 is this black line here. 2345 BC. And this is the year 2000.
Which would be about the time of the flood,
Right.
according to the Masoretic text.
Yeah. Yes.
And I'm assuming that people have done physical, using those ancient tools, have done physical measurement checks to essentially establish a maximum degree of error. Because that, I imagine that might be an argument here, but if the actual tool itself is relatively accurate, even if simple, then that would counter a...
Right. So what Dodwell did was he actually went through all of the ancient measurements, and so that's what he thought. He thought that that when he first found this, he thought that he was running into measurement error, and so he went through all of the measurements, and he corrected for things like parallax. He corrected for the edge of the sun casting a shadow rather than center. He corrected for everything he could think of correcting for. And this is the data after he's corrected it as best he can. And okay, so here's the Great Solar Temple of Amun-Ra at Karnak, Egypt. This is an interesting case. When the Great Solar Temple was built in Karnak, it was oriented to the sun in a way that showed that the obliquity of the ecliptic was 25 degrees 9 minutes 55 seconds, or 1 degree and 14 minutes greater than predicted by Newcomb's formula. So that has been a point of a bit of contention. When the temple was first surveyed very carefully, some of the researchers said this was never designed to be oriented to the sun at all, because because it lies outside of the realm of possibility for where the sun would have ever come up in the morning. But if you look at the archaeology of the temple, it was clearly designed to be a solar temple, where the sun was designed to come down a passage and light up this idol at the end of a very long passage, once a year at the summer solstice. So anyway, there was a discrepancy between what the archaeologists were finding in the orientation of the temple and what they were seeing in the actual design of the temple itself.
Do they know when the temple was built?
I think they do know pretty well. Yeah.
Well, actually, that's
Okay. Yeah.
going to be a matter of dispute too.
Right. Well, some of the first guys actually said that the temple was built something like 4000 BC because of the orientation, but even putting it at 4000 BC doesn't put it back far enough on Newcomb's formula so that the sun actually makes it down the corridor.
Yeah.
But the orientation of the temple was the reason for putting it back so far in the past. Okay, so even if modern calculations were correct and the temple had been built at the maximum value in 6000 BC, we would only expect it to show a value of 24 degrees 11 minutes for the obliquity of the ecliptic, not the 25 degrees 9 minutes, almost 10 minutes. So now if looking at this graph, it looks like the maximum value is 8,000. That's 8,000 years ago, which would have been 6000 BC. And this is based on Stockwell's calculations, which were more extensive than Newcomb's. Okay, so here's the effect of the change of the obliquity of the ecliptic on the solar temple of Amun-Ra at Karnak. So you have, so this is where we are now at S1, well, 1936, when they were doing some of this, when I think Dodwell was probably writing. 320 BC, that was when the Ptolemaic pillar was constructed, and it's out of alignment with the with the rest of the temple. 1579 BC would have been right here, and it would have just barely made it back to this altar. And then at the construction in 2045 BC, it would have been straight down the corridor. So these dates are using Dodwell's curve. If we don't use Dodwell's curve, we're just off here and we never even get the sun down the corridor. So someone might say, well, maybe there's tectonic plate motion, maybe the Egyptians were not good at orienting things. This one fact should dispel both of those ideas. That the Great Pyramid is squared to within 4 cardinal compass points to within 1/300th of a degree. So no, they knew exactly what they were doing. So they knew how to orient buildings with extreme precision. There's been no tectonic activity to disrupt the data. The orientation of Karnak was not a fluke and represents real data. And the value for the obliquity of the ecliptic derived from the Temple of Karnak is greater than any possible value predicted by Newcomb or Stockwell's formula at any point in the past. So I think those taken together make an interesting case. So then we'll talk about Eratosthenes for a bit. So when he undertook the calculation of the Earth's circumference in 230 BC, he and his helpers surveyed the winding south-southeast to southeast route from the well in Aswan to the tower in Alexandria with such precision that he calculated the distance between the two latitude parallels as 489.33 miles. The actual distance is 489.75 miles.
So that's pretty good.
He did all right. And when he completed his investigation, his estimate for the polar circumference of the Earth was only 199 miles less than the currently accepted value. Which, it's amazing that guys with using sticks as tools were able to do this. Just before modern machining, before telescopes, before any of the precision, anything that we would think of as a precision instrument. When Dodwell's corrections, parallax, refraction, and accounting for the shadow cast by the sun's edge rather than its center, are applied to Eratosthenes' calculations of the latitude of the library at Alexandria, the given latitude is 31 degrees, 11 minutes, 52 seconds. Modern observations give a latitude of 31 degrees, 11 minutes, 50 seconds, an error of only 31 meters. So his GPS skills were quite good. Eratosthenes took great care with his astronomical measurements. He carried out his work over several decades. He noticed that the obliquity of the ecliptic had changed over the preceding centuries. And again, Eratosthenes' measurements represent precise, accurate data. So looking at that graph again, we have quite good data then from Eratosthenes from a couple hundred years before Christ, which is significantly deviated from what we would expect based on Newcomb's formula. So one of the ways to test this is that one prediction of Dodwell's work is that the astronomical orientation of these sites should give an older date using Newcomb's formula than the archaeological evidence should give us. And you may have run into some discrepancies in what people say about Stonehenge. And it's because of this precise issue where people will look at Stonehenge and they'll say, oh, it's, they look at the astronomical orientation and they'll say, oh, it must have been built between maybe 1600 or 1900 BC. But the archaeological evidence gives a date of a few hundred BC. So using Dodwell's curve, we can actually see that this brings the astronomical date right in line with the archaeological evidence.
Which is a fairly strong
That's a strong argument. Yeah. Yeah. Tiahuanaco is in Bolivia, not too far from Lake Titicaca. And this one has not been surveyed as extensively as Karnak or Stonehenge, but using the surveying that has been done, it would appear that the construction date based on Newcomb's formula would have been about 4000 BC. And archaeologists have problems with that for a number of reasons. But if you use Dodwell's curve, that pulls it up to 700 BC, which is completely in line with what archaeologists might expect. So again, another interesting bit of data confirming Dodwell's hypothesis. Okay, so explanations. One is a comet or asteroid strike. Now this one is hard to imagine because the Earth is so big. The Earth has so much angular momentum. I think, I have not done the math, but I think that if we were struck by an object big enough to make that kind of dent in Earth's obliquity, in the obliquity of Earth's ecliptic, it would, I just think it would utterly destroy the planet. And it'd be so much worse than the hypothesized dinosaur-killing meteor. Yeah.
Is there any kind of, I guess, since this was described as a wobble correction, so if we took the oldest data point, is there any kind of calculation for the energy requirements to cause that offset in the first place, given that what we think the trend should be?
Well, so this is actually one of the things that I think we ought to work on. So I would say no. John Baumgartner worked on it for a while, and he gave up on this. But I think we need to work on this more. Something that John did show is that if you shift the mass of a spinning object, so you have a spinning object and you shift the mass inside of the object, you can create a wobble. So that to me sounds more plausible, and I wonder if catastrophic plate tectonics was enough to create a wobble. And if that wobble then may have affected Earth's magnetic field orientations. Because I would say that, I mean, we have no clue why the magnetic field switches poles. That's the hypothesis that I would start working on.
I was just going to say, that might also be a good, like if you do get the energy calculation for what a strike would require, and it's definitely biosphere lethal.
Right.
And that does kind of only leave something like catastrophic plate tectonics.
Yeah. Yeah. So Dodwell's conclusions were that the anomalous variation from Newcomb's formula covers 4,194 years from 2,345 BC to 1850 AD. Prior to 2345 BC, the Earth might have been tilted at about 5 degrees when something happened that knocked it to 26 degrees. And this event caused the Genesis flood.
Wow, 21 degrees.
Yeah, yeah. Yeah, it's hard to imagine. And I mean, and you think about this, if you've ever played with a spinning bike tire gyroscope, it's a lot of work to move it one direction or the other, and then imagine how much work you would have to apply on the Earth's axis to get it to shift that far. And especially, and how much upheaval that would cause in a sphere that is not exactly so. It's not solid. It's at the scale of the Earth. It's not solid at all. My conclusions: I think Dodwell made an excellent case for the reliability of ancient measurements, and they vary considerably and in a predictable fashion from Newcomb's calculations. I do think this data needs to be researched rather than dismissed as incorrect, which I've talked to a few people, and some people just want to just toss this out and forget that it ever happened. On both sides of the argument, because it is difficult to deal with, I think. I would say connecting the biblical flood with this event is reasonable, and the resultant curve gives us a way to test the ages of other ancient observations, and that would be something that we could put some more work into And again, the best explanation I've seen for the data is Dr. Baumgartner's catastrophic plate tectonics theory.